Great pleasure to introduce Professor Onur Mutlu and to welcome him virtually to Texas State. Despite his very young age, he's had an extremely impressive career already. He only got his PhD 14 years ago, but his work has already been cited over 31,000 times, and he has almost 100 papers that have at least 100 citations. Interestingly enough, his research career started just down the road at UT Austin, which is where he got his PhD. Then he worked for Microsoft, Intel, AMD, VMware, and Google before becoming a professor at CMU in Pittsburgh. And now he's a professor at ETH in Zurich in Switzerland, which I'm particularly excited about since that's my alma mater. So his research is very broad, as you can imagine, but it mostly encompasses computer architecture, systems, security, and bioinformatics. And he literally has too many awards for me to go through all of them. He has many early career awards, technical achievement awards, loads and loads of best paper awards. He's a member of the Academy of Europe, a fellow of the IEEE, and a fellow of the ACM. And I'm just very pleased to have him here, and I look forward to his presentation on intelligent architectures and intelligent machines. Onur, it's all yours.
Thank you very much, Martin, for the very kind and humbling introduction. I wish I could have been at San Marcos to give this talk, actually, but clearly that's not going to happen this year. But I have fond memories of going there while I was at UT Austin, for sure. It's a beautiful town, I think. Okay, can you see my screen? I just shared it. I'm going to put it into presentation mode. Okay, cool.
Yeah, perfect.
Okay, great, thanks. So as Martin mentioned, I'm going to talk about intelligent architectures for intelligent machines. This is a broad talk, and I will first start with saying that I'm partly responsible for this title. I was invited to give a keynote at one of the funding agencies in the US at some point in 2019, and I was too late in providing my talk title. So somebody decided for me that I should be talking about architectures for intelligent machines, and I really liked that, but I wanted to add intelligent to the front. So since then, I've been giving a talk titled "Intelligent Architectures for Intelligent Machines" for some time now, and it's evolved into something hopefully interesting to keep you busy for about an hour or so. I assume we have about an hour or so, right, Martin?
Yeah, that's exactly right.
Okay, yeah, because I planned for 3 hours. I'm just kidding. There's material for probably much more than 3 hours, but I'm going to skip some slides and hopefully we'll cover interesting things. But feel free to ask questions in the meantime. So the problem we're seeing today is computing is bottlenecked by data. And data is clearly key for many interesting applications. All important workloads are data intensive, AI, ML, genomics, pick your favorite application. It's going to be hard to find something that's not data intensive, that's really stressing the computing resources that we have today. And these workloads require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. Today, we can generate more data than we can process. And you can imagine this in workloads that we have been used to so far. These are some workloads that we claim to understand more than some others. And data is a performance and energy bottleneck in these workloads, and it overwhelms modern machines. And even on the mobile end, we see workloads that are stressing the machines quite a bit. And these workloads are increasingly stressing the machines, and they're overwhelming modern machines. And some emerging workloads like genome analysis workloads are going to be stressing the machines even more, I believe, because today we can generate much more genomic data than we can actually process within some reasonable time, because the cost of sequencing has been reducing significantly over the years. And this is a fascinating topic that I do work on, and I'll briefly mention this over here, but you can imagine more interesting workloads and systems that can do genomic analysis within real time. Today, actually, you can have mobile devices that can do genome analysis. But today, the key point is sequencing is not a problem. But the analysis that comes after it, which is computational analysis to reconstruct the genome and to do analyses on the genome, to ask questions like, what treatment should I deliver to this patient? What kind of genome is this COVID-19 genome similar to or dissimilar to? And the scientific discovery and essentially medical advice is limited by how fast we can do this analysis. And it's mainly because data is a performance energy bottleneck. And this is one of the devices, it's relatively old right now, that you can use to do this analysis in the field. People are using this device in Africa, for example, to look at the new viruses, and in other places also. And actually, this is very instrumental for COVID-19 genome analysis today. And we do a lot of work in this area. And basically, our goal is to design devices that can do the analysis on the spot within real time, so that you can answer very sophisticated questions within a minute or less, if you will. And if you're interested in this, I'm not going to go more into detail of this, but we recently published a paper that covers a survey of a lot of the work. And it's a relatively short paper to read in short format. So I'm happy to talk about it. And this is another paper that we have recently published looking at specialized accelerators for genome analysis, focusing especially on the approximate string matching problem, which is at the core of many genomic analyses that you have to do. It actually feeds a lot of downstream analysis that you have to do. Okay, I don't want to talk more about this, but this is an example of application that overwhelms modern machines today, and the use cases that we're envisioning can overwhelm future machines even more. Basically, the problem is really data in the end. Data overwhelms the storage and memory capability, communication capability, and in the end, computation capability of modern machines. It also impacts greatly robustness, energy, performance, and cost. And if you go back to the fundamentals, a computing system consists of three key components. You need to have computation, communication, and storage and memory. And in the grand scheme of things, we're very processor-centric today. Today, data has to go to a computing unit so that it can be processed, and everything else is relatively much less optimized and clearly not intelligent because they don't have the ability to process the data. And if you look at this picture, this is my drawing from 2008 or so when I was writing NSF proposals at the time. This is a proposal that was sent to NSF. But this drawing still holds. But basically what this drawing shows is computation units are the red parts, and everything else is doing data storage and movement. And if you do the calculation, less than 5% of the hardware resources of a single node, including everything in the node, is dedicated to doing computation. Everything else is dedicated to storing and moving data. And this is because we have a processor-centric design, and everything serves the processor in the end. Okay, and we call these things computing devices, but maybe we should be calling them data storage and movement devices. And that's a reflection of data overwhelming modern machines. I'll give you one other data point. We analyze these workloads together with Google, and these are clearly Google's workloads that are used in Google's mobile devices. And we found out that more than 60% of the total system energy in these workloads on a cutting edge processor and a system on a chip is spent on data movement. So we will get back to this. Basically, energy is also bottlenecked by data movement today. So I will start with this axiom, basically. Today, an intelligent architecture needs to handle data well. So of course, the question is, how do we handle data well? I believe this has three components. First of all, we need to somehow ensure that data does not overwhelm the components. And to be able to do this, we need to design intelligent algorithms that minimize data movement, intelligent architectures that minimize data movement, and probably more importantly, we need to design whole system designs all the way from algorithms to architectures and devices that minimize data movement. And I'm going to talk a lot about this part in this talk. On top of this, I believe the architecture has a second characteristic, which is we need to take advantage of vast amounts of data and metadata, and we don't do this well today. Basically, there's a lot of data that flows through a machine today that can be used to improve the architectural and system level decisions that are made in the architecture, but that is not today used for that purpose. For example, I will give you an example from my cell phone, which is 5 years old. It has a memory controller, that's a hardware memory controller that accesses memory. For 5 years, it's executing exactly the same algorithm. It has not learned anything at all from what is seen. Basically, it cannot judge whether it's made the correct decision or the wrong decision to optimize some long-term metric. In fact, it can decide on this if it were designed to be learning, meaning intelligent, meaning potentially it could have a machine learning algorithm, for example. Reinforcement learning is a good fit for this. It could have made much better decisions very quickly. As humans, we can do that, right? We put our hand on a stove and we quickly say that if the stove is hot, we're not going to touch that stove. But our machines at the very basic level are incapable of doing that sort of learning. And as a result, I believe we're losing a lot of opportunity. So that's the second part. And the third part is, I think, very important as well. Today's architectures do not understand and exploit properties of different data very well. And I believe to handle data well, we need to be able to do this to improve the algorithms and architectures and various metrics. For example, in the general purpose systems, the communication between the software and hardware is reduced usually to memory addresses and some bits, essentially instructions. But the semantic properties of the data is not communicated. For example, what kind of semantic properties do you want? Privacy of the data, privacy properties, privacy requirements, security requirements, compressibility requirements, even locality requirements are not really provided to the underlying architectures in a good way today, in a general purpose way today, so that the architecture can make good decisions. Okay. So corollaries based on the previous slide, I've already discussed a lot of these actually, but I believe today's architectures are not good at dealing with data. They're designed to mainly store and move data as opposed to compute on the data. This is because they're very much processor-centric as opposed to data-centric. So we're going to talk a lot about data-centric architectures today. On top of this, architectures are not good at taking advantage of vast amounts of data and metadata available to them. They're designed to make very simple decisions, ignoring lots of data. And as a result, they are not foresighted. They cannot change their policies based on potentially wrong decisions they make at the very hardware level. This is because they make human-driven decisions as opposed to data-driven decisions. A human designs the components, and humans by nature cannot take into account hundreds, if not tens of things, actually. As a result, the decisions end up being very simple, and data-driven decisions that are based on learning algorithms could be much better. I hope I will be able to get a chance to give examples of this, but let's see. Within 1 hour, it may be difficult. On top of this, I think architectures are not good at knowing and exploiting different properties of application data. They're designed to treat all data as the same, except for specialized cases where you need to go through very special interfaces or specialized accelerators, which do this at a limited level. This is because they make component-aware decisions as opposed to data-aware decisions. So if you look at a cache today, for example, it's a component. It doesn't really understand the properties of the data very well because it doesn't get enough communication about for example, the security properties of the data. This is because there's no interface that's allowed to do this sort of general purpose communication. So hopefully we'll get a chance to cover this, but I'm not sure. So let's see. So we'll start with this first one. We'll talk a lot about data-centric architectures today. I also call these memory-centric architectures. If I have to list the properties of a data-centric architecture, these are the 4 key properties that come to my mind. First of all, I believe if you are data-centric, you need to really process data where it resides. You need to minimize data movement. I also call processing data where it makes sense, basically. I'm going to talk a lot about this. And if you're data-centric, you really need to respect data and how you access data. And it has to be low latency and low energy. And I think we're not doing a good job in terms of having low latency and low energy access to vast amounts of data. So we need much better approaches to low latency main memories and low latency storage devices plus low energy. I'm not going to talk a lot about that, but this is very much synergistic between processing data where it resides. So if you're close to a storage device, for example, and if you have high latency, then that's probably not good. On top of this, we want to have low cost data storage and processing. I'm not going to talk a lot about that, but hybrid memory, compression, having high capacity memory at low cost are good examples of this. And I believe a data-centric architecture should intelligently manage data, should have intelligent controls handling robustness, security, cost, etc., other metrics. And we're going to touch upon this actually to motivate processing data where it resides, because these are, I believe, all synergistic with each other. By the way, the data-centric, data-driven, and data-aware architecture paradigms are also synergistic with each other, as we may get to discuss later on today. Okay. So let me jump into processing data where it makes sense. Essentially, today we're processing data only in the processor and the accelerators because we're very processor-centric. Why don't we process data wherever data is and whenever data moves? Clearly, this is an old idea. We're not the first one discussing this idea. And if you actually go back in literature, in general purpose computing, processing in memory was first proposed by this work, as far as I know. Please correct me if you find some other work. but this work was written by Harold Stone based on the work that he had done in the late 1960s at Stanford. And he basically proposes having a cache that can do processing in it so that we don't go to memory, so that we don't increase the ping count to memory. So this was actually a very foreshadowing paper at that time, but exactly the opposite of what he wanted happened. We had the processor memory bottleneck, and we clearly didn't increase the ping count on our processors and memory. So what he feared did not happen, but in a sense, what he feared happened because we had this huge huge memory bottleneck. Because logic in memory computer did not happen at that time. So why is it interesting to examine today? Clearly, this idea was proposed in the 80s, and the 90s, and the 2000s, again and again. I believe today we're in a special place because we have a huge push from technology pushing us to do something different, because DRAM is not scaling very well. I will briefly cover this. And then we have a huge pull from systems and applications that I will also cover. Let's cover the technology and circuit and device push. So DRAM is the main technology that's designed for main memory today. And today, DRAM scaling is not going well. In fact, we're having a lot of problems. As a result, industry is open to new memory architectures, as I will discuss in a little bit. So these are some of the architectures, 3D stacked memory architectures that contain logic layer that can do processing very close to memory with high bandwidth, low latency, low energy access to memory layers. And these are some other example opportunities that are being exploited by industry, at least in experimental settings. So why are these motivated? Because memory scaling, technology scaling in memory is actually becoming much more difficult. This is an invited presentation that I delivered at the International Memory Workshop, which is mainly an industry-dominated workshop, where we foreshadowed a lot of the memory scaling issues, saying that we should be more data-centric. And at that time, we didn't have a lot of evidence in terms of the technology scaling that's hitting DRAM. But later we collected a lot of evidence. This is one example evidence that I'm not going to go into a lot of detail, but we analyzed all of the memory errors that Facebook has in all of their data center servers worldwide. And this is a lot of memory errors, a lot of servers, a lot of computation units. And the key takeaway is the chip density that's employed in your server has a very strong correlation with the server failure rate that you see in the server. This is the chip density of the DRAM chip. And this is because cells are getting closer to each other and they're becoming more vulnerable to noise, and they're seeing more errors in the field, essentially, while doing operation. If you're interested, you can take a look at this paper. And we also, at the same time, wanted to study these errors, these reliability issues in DRAM at a very low level in a controlled manner. So we designed FPGA infrastructures to test retention issues, for example, or other reliability and latency issues. And this is one of the versions of the infrastructure. And this is one of the newer versions where we released to the community. So if you're interested in doing DRAM testing studies, other folks are using it both in industry and academia. And we actually released the C++ API so that you can actually do this without knowing a lot of RTL knowledge. And if you're interested in using it, we'd be happy to support it, actually. So while we were doing a lot of experiments, one thing we discovered together with Intel was that in memory devices and DRAM devices, you can actually predictably induce errors today. And this happens in most DRAM memory chips that we tested. So clearly this should not happen. You should not be able to induce any errors in a predictable manner in DRAM chips, because this could be a security problem, as we will discuss. So this is now known as the RowHammer problem. And more than 80% of the tested DRAM chips were vulnerable to this effect. And it's as far as I know, the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. Because if you can predictably flip a bit, you can use that bit flip intelligently if you're a hacker, let's say, so that you can gain control of the entire system. And later, other folks show that you could do that. And this is one popular article saying, forget software, now hackers are exploiting physics, which is, I believe, a very nice high-level characterization of what is happening with RowHammer. So what's the problem? Essentially, if you know memory, the underlying problem is a read disturb error. Whenever you're reading a row in DRAM, you're disturbing adjacent rows. And this is a very fundamental problem. And we know that other memories are prone to this. SRAM is prone to this. Hard disks are prone to this. Flash memory is prone to this. In fact, we do a lot of work on flash memory, and we observe this many, many times. But DRAM is very special because it's directly exposed to your programming language and your operating system and your software. So if you get a bit flip in DRAM, it directly affects your data structures. So it should really not happen in DRAM. It should not be exposed to the user in DRAM, let's say. So the problem is when you activate a row in DRAM, if you want to read something in a row, in a memory row, you need to activate that row. If you want to read something else in the same bank, you need to deactivate the row. In DRAM, the first command is called activate. You apply high voltage. The second one to deactivate is called precharge. You apply low voltage. Now let's assume a program or some design that does this repeatedly. Activate, precharge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, repeatedly enough times before the cells get refreshed. It turns out in modern DRAM chips, you can do enough of these hammerings to cause bit flips in these physically adjacent victim rows. And we showed in our 2014 paper that more than 80% of the chips that are manufactured by the three major DRAM manufacturers, there are only three major DRAM manufacturers in the world today, are vulnerable to these effects. And this is a scaling problem. Basically, the chips that were manufactured between 2008 and 2009 and earlier did not have this problem. But the first appearance in 2010, and all of the chips that were manufactured between 2012 and 2013 that we tested were vulnerable to this effect. So it became a scaling problem because over time, cells became closer to each other. And the effect of electromagnetic coupling that you induce by doing one activate now became much stronger over time because the cells are closer to each other and the noise became worse. And also, as a result, one could induce enough activates to cause these bit flips within a refresh interval. So if you refresh memory much more frequently, this problem goes away, but refreshing is not a good idea because that actually consumes power and clearly it impacts your performance. So over time, the scaling problem will get worse. I'm going to give you recent data from our 2020 works, actually. So this is actually concerning from a reliability perspective, clearly, but it's more concerning from a security perspective, potentially. When we first wrote the paper in 2014, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I believe this strongly. And we said in the paper that one could actually take what we did and write an attack program that could hijack your computer completely. And while we were working on that, these good folks from Google Project Zero showed exactly that in 2015. They basically said that they learned about the problem from our work, and they basically replicated the problem, and they constructed a beautiful security engineering attack that takes over x86-64 Linux using a user-level program. I'm not going to go into the details, but I would recommend you take a look at their blog post, and they have a Black Hat USA presentation on this. So how do you solve the problem? Again, I'm not going to go into the details of this, but one solution is having slightly intelligent memory controllers that can understand that something not good is going on and that can refresh the adjacent rows of potentially hammered rows. Our solution was probabilistic, actually. A probabilistic solution once in a while refreshes the adjacent rows of rows that you're activating, and that solution was employed in some Intel memory controllers. But then later, DRAM manufacturers said we have a solution to RowHammer, and as a result, Intel took it out of their memory controllers or disabled it in their memory controllers, and we are left with DRAM manufacturers having a security solution. So let's take a look at how things fared after that. So basically, memory scaling issues are real today. We have RowHammer as a prime example of this. If you're interested in a retrospective that was invited and that we wrote in 2019, this covers a lot of the work spanning the architectural research, security attacks, device level research, popular press, etc. Unfortunately, what it doesn't cover is the work in 2020, which I'm going to briefly talk about, because things have not become better in 2020. Essentially, as I said, this is a scaling problem, and the cells are becoming smaller in newer devices, and those cells are becoming closer to each other, and as a result, things are becoming much worse. So these are the key takeaways from our ISCA 2020 paper. We essentially analyzed more than 1,500 chips, and we found out that chips of newer DRAM technology nodes are more vulnerable to RowHammer. And there are chips today whose weakest cell fail after only 4,800 hammers. And this is very worrisome because when we first wrote our paper, this number was 139,000. So now you can actually hammer only 4,800 times and get these bit flips. So it's much easier. The barrier to getting a bit flip in DRAM is much easier, much lower. And you can actually induce these bit flips in more rows and farther away from the victim row. And even worse, perhaps, is that the existing mitigation mechanisms that are proposed in academia are not effective when you go down to 4,800 hammers. So we have a problem, essentially. The problem is becoming worse because it's a technology scaling problem, and the jury is still out in terms of solving the problem. So what is worse is, unfortunately, the solutions that DRAM manufacturers promise to be RowHammer free very publicly are proven to be not RowHammer free. So this is a work that we published in Security and Privacy Conference this year. And we basically showed that the solution that is put inside the DRAM chips that is not disclosed to the public can be reverse engineered, partially at least, and can be reverse engineered enough so that you can actually mount an attack that induces bit flips in the presence of the solution. So I'm not going to go into the detail, but basically this shows that existing DRAM chips that are advertised as DRAM RowHammer free are not RowHammer free, because you can do what is called many-sided RowHammer attacks. You can hammer enough rows in a DRAM chip enough times such that you overflow the underlying hardware protection tables that are inserted into these DRAM chips by the manufacturers. And as a result, you're back to square one. These chips are not secure. And these two works actually caused some churn in industry. And as a result, DRAM manufacturers plus big companies are discussing how to actually solve the RowHammer problem going forward. So there are new JEDEC research groups that are formed actually to solve the RowHammer problem. There's actually one more work that is actually very interesting, in my opinion. We've tried in this work to show, answer the question, can we somehow validate via testing whether a chip is RowHammer free or not? And the answer is no, basically. As far as we know today, there's no testing methodology one can develop, at least we couldn't develop it, where you can answer the question definitively, which is concerning also, clearly. That's a question we would like to be able to answer when we're doing testing and validation of chips. Okay, so I think the solution to these things, to this sort of scaling issue, is really by having more intelligent controllers that cover up for the fact that memory is not perfect, but intelligent controller can actually solve some of these problems by doing intelligent refreshes and understanding when a potential attack is happening potentially. And we're not the only one who's proposing the solution. It's industry is also looking into. There's a 2014 paper by Samsung and Intel on the memory forum that says that you need to co-architect memory controllers and DRAM so that you can handle some of these scaling issues. And this is not just with RowHammer. Actually, retention, data retention is a big problem in DRAM. The refresh rate is increasing, and solving the refresh rate, I believe, requires an intelligent memory controller. Today, for example, we refresh everything in DRAM every 64 milliseconds, even though the underlying device doesn't require that much refresh rate. For example, there are many cells that can be fine without refreshing every 256 milliseconds. There are only a very small fraction of cells that will lose their charge if you don't refresh every 64 milliseconds. But to be able to understand which cells should be refreshed at which rate, you need an intelligent memory controller to detect this. And we've been looking into this problem for more than 8 years now, actually. And I'm not going to go over all of these solutions, but all of these solutions actually point to the fact that you need an intelligent memory controller to be able to handle refresh intelligently and to get rid of refresh as much as possible. Okay, so hopefully I've convinced you that we would like intelligent memory controllers to solve scaling issues in memory. And again, this is not a new idea in the general sense. Flash memory, for example, already employs very reasonably intelligent memory controllers to cover up for the fact that most of the flash bits don't work out of the factory. And as I said, industry is writing papers about it too. This is a paper that's written by Intel and Samsung, two companies that otherwise don't talk to each other as much. But they were nice enough to write this paper to our memory forum, and we invited them to participate. And they said that DRAM process scaling is becoming worse, and we want to co-architect controllers and DRAM and make controllers more intelligent to hopefully make DRAM process scaling better into the future. Okay, so that's one side of the story. We have a huge push from technology today to do some have some intelligence in the memory controller. And I think the next step in intelligence in the memory controller is doing computation in the memory controller. But let me give you the higher level story also to show you that we're kind of squeezed in the middle today as we have never been before. So this kind of push from technology we've never felt in the past, not 10 years ago, or not even 5 years ago almost. When our first RowHammer paper was published, it didn't receive a lot of attention. Only after it became a security attack vector, people actually saw that it was a big problem in technology scaling. So let me talk about the pull from systems and applications. So let me go to the next slide. Today, data access is a much more major bottleneck than it was before because applications are increasingly data hungry. Energy consumption is a key limiter, and data movement energy dominates compute energy. And this is true, especially for off-chip to on-chip movement. In my opinion, the question is this: do we want a future that is much more sustainable, energy efficient, and beautiful, where we can breathe? Or do we want a future that doesn't look as good like this, but it may be very productive? My answer is we would like the best of both worlds, basically. We don't want to give up high performance and productivity, but we would like that to come with energy efficiency and very long-term sustainability, as well as short-term sustainability. And I think in computing, the power, the energy consumption of computing is growing significantly over time, and the sustainability impact of computing is growing significantly over time. I'm not going to quote numbers, but there are numbers that are increasing over time, especially for cloud computing, for example, today, data centers. And at the very basics of computing, data access is the major performance energy bottleneck, and we're not handling it well. Our current design principles cause great energy waste because we're not handling data in a data-centric manner. We're bringing everything to the processor, and that is causing a lot of energy waste, and that is causing a lot of performance loss. But we try very, very hard to mitigate that performance loss by adding a lot of complexity into our systems. We design our processors to be out of order, heavily multi-threaded, in GPUs, for example, many levels of caching, complex hierarchies, complex prefetching mechanisms. In the software, we make software more complex to avoid the data movement sometimes. And as a result, we mitigate some of that performance loss, but we don't mitigate a lot of it. But what we add is really even more energy waste, especially when these techniques don't work. When these techniques don't work, we're actually in a very much vicious cycle. We try to overcome the performance loss of the data movement bottleneck by wasting even more energy, and data movement bottleneck by itself wastes a lot of energy. So we're in this vicious cycle. And whenever we're in a vicious cycle, it's good to understand why that vicious cycle is caused. And I believe the answer is clear in this case, because we're processing data far away from the data. And I showed you this picture before. I'm not going to repeat it, but I'm going to talk about the fact that processor-centric memory systems is the reason for this peril, let's say, because we cannot process data anywhere else in the system. We're bringing data all the way into the processor and the accelerators, and that's causing the processor to be more complex, as well as the system to be not so efficient. Yet we know very well that memory is a big bottleneck. This is a quote from Dick Seitz. He was the chief architect of alpha processors in the 1990s. And after his team designed one of the fastest processors of its time, he wrote this one-page article that was published in Microprocessor Report that's entitled this way: "It's the Memory Stupid," clearly playing on the elections that were going on in the US at that time frame. But basically in this paper, he said that we designed this alpha processor, cutting edge, to finish 4 instructions per cycle, but it's finishing 1 instruction every 4 to 5 cycles in this important database workload. Essentially, it's operating at 1/16th to 1/20th of its bandwidth, which doesn't sound good. Why? It's waiting for data. And he basically finished the article with the sentence: "I expect that over the coming decade, memory subsystem design will be the only," emphasis from him, "important design issue for microprocessors." And I agree with him, and I think we need to really take this more seriously going into the future. This is data from my own PhD thesis. We worked together with Intel to analyze all of the workloads that they used to design their microprocessors at the time. And we found out that more than half of the time, the processor is waiting for data, very similarly to what Dick Seitz found out for his alpha machine 10 years ago. And if you're interested, you can read the paper that we wrote. Okay, you don't believe me, maybe you don't believe Dick Seitz. Since everybody believes Google today for whatever reason, Google published this beautiful paper in 2015, in ISCA 2015, where they showed essentially the same thing. They analyzed, according to them, all of their data center workloads that is executing their data center. And they basically said the processor is waiting for data most of the time. It's doing useful work only 10 to 20% of its time. And this is a cutting edge Intel processor that they employ in their data centers. And if you're interested, you can read the paper, which is referenced at the bottom over here. And it's a beautiful paper that I cover in my classes. Okay, so all of this is happening because we have a grossly imbalanced system, because we're very much processor-centric. And I think processor is just one instance of an accelerator. If you can put your favorite accelerator over there, also a machine learning accelerator, and maybe GPU as well, which is essentially imbalanced in the end. And imbalanced system, because processing is done in only one place, this is energy inefficient, low performance, and complex. And on top of this, we add more complexity to tolerate the performance bottlenecks, and that makes system even more energy inefficient and complex and low performance, because we could have used all of that real estate for actually improving performance as opposed to tolerating data access latency. As a result, we're back to the picture that I showed you earlier. Most of the system is dedicated to storing and moving data. Let me give you the energy perspective very quickly. I already gave part of it, but I'm going to borrow a slide from Bill Daly from his HighPeak 2015 keynote. All of these numbers have changed, but the key order of magnitude remains almost the same. Basically, he compares a 64-bit double precision floating point operation energy, 20 picojoules, a 16 nanojoule, and a DRAM read or write, which is 16 nanojoules. That's 800x difference. So it's good to ask the question over here, if I don't have a lot of locality, does it really make sense to bring data into the processor to actually do the floating point operation and then write the data back into the processor into the memory after that? Okay. And my answer would be no, it doesn't make sense. But okay, if you look at the numbers, a memory access today consumes about 2 to 3 orders of magnitude the energy of a complex addition. And to be able to overcome that, you really need to have a lot of locality in your workload to be able to exploit the caches. Okay, and as a result, we have this picture that I mentioned earlier. More than 60% of the total system energy spent on data movement on important workloads that we all use in our mobile systems, for example. Basically, I will argue that we do not want to move data. And I believe we need a paradigm shift to enable computation with minimal data movement, compute where it makes sense, where data resides, in other words. And we want to make computing architecture more data-centric. And as I said, processing where it makes sense is one property of a data-centric architecture. And I think memory, I will talk about processing inside memory, but this general idea is applicable to processing inside the caches, processing over the interconnect, processing in the storage device. I think memory is very, very interesting because...
Can I ask you a question?
Yes, please, go ahead.
Will you go as far as computing in the memory?
Yes, absolutely.
Using the memory as an ALU?
I'm going to give you using the memory as a bitwise computation engine. Yes, you could call it an ALU. Okay, so I'm going to talk about that. I'm going to talk about DRAM, but you could actually do even more in non-volatile memory technologies. But yes, I'm going to talk about that as one example. We call it processing using memory. But also, I'm also going to talk about processing near memory as well. I think these are both more data-centric systems.
Thank you.
Sure, you're welcome. I think memory is a very special place today because we can actually fit a lot of workloads in memory databases, in memory graph processing engines, in memory media processing engines. Workloads are optimized to actually fit in memory today, which is very good. And actually, I think memory is one of the hardest places to actually do processing because you could potentially do processing inside storage, you could potentially add processing elements inside the cache, but today's memory technology, DRAM technology, doesn't go well with integrating logic into it, except for 3D stacking, for example. So there are many questions in this general direction. Clearly, we would like to be able to query memory, ask questions to it. Memory, can you execute this function for me? And memory is going to hopefully provide results if it says yes. Otherwise, it may defer the processing somewhere else. But there are many questions. How do we design the compute-capable memory and controllers, processor-dependent memory units? How do we design the software and hardware interfaces for this? How do we design the system software compilers and languages to take advantage of a particular processing in memory design? And on top of this, how do we change the algorithms and even think about theoretical foundations of computing? I'm going to talk about that briefly. Essentially, this is all the way from algorithm to devices co-design problem, and we need to really revisit everything to be more data-centric in between to actually take advantage of the data-centric paradigm to its fullest extent. But of course, we need to be also practical. We need to look at very simple modifications to enable practical mechanisms as well. So I'm going to talk about both directions, if you will. But I'm going to make a comment since we're talking about computer science over here. The theoretical foundations of computing theory of complexity is based on counting operations. Essentially, if you look at complexity theory, it really counts operations. But I will argue that that's a very processor-centric way of thinking about computing theory. If you're more data-centric, maybe you should be thinking about how much you're moving data to really understand the complexity of algorithms, for example. I believe you need to do both in the end, but today's theoretical foundations of computing is very processor-centric as well. Okay, so let's talk about processing in memory. So in the past, people have proposed putting a processor inside the DRAM chip, for example, and I don't think that's an idea that's going to work really well because these two technologies are fundamentally not so compatible. Although there are limited examples of this that's being investigated in the industry today, and we're working with those folks. I'm going to mention that briefly. I think we need to think a little bit differently also. I'm going to talk about thinking differently. One is the direction of using memory for processing as much as possible by minimally changing the memory chips. And the second direction is taking advantage of 3D stacking technology. So let's talk about the first one. I'm going to give you examples from DRAM, but the ideas that I'm going to propose are actually applicable to other technologies like SRAM, as well as phase change memory and non-volatile memory as well. Essentially, I believe all memory chips have great capability to perform bulk data movement and computation internally with very small changes. You can exploit internal connectivity to move data, and you can exploit analog computation capability that exists in memory chips. I'm going to give you some examples of this. I'm going to start by cheating, meaning I'm not even going to talk about computation or ALU, as you mentioned. I'm going to talk about data copy initialization because it's very important, in my opinion. There are many applications that do a lot of data copy initialization. Imagine a 1 terabyte database. Initialization of that database physically, in physical memory, takes a lot of time. And this is especially felt in virtual machine cloning, forking, zero initialization for security. You can imagine many things. Again, if you don't believe me, since everybody believes Google for some reason, Google, in their beautiful paper in ISCA 2015, they said that 5% of the cycles in their data center workloads, all of their data center workloads, is spent just on these 2 function calls, memmove and memcopy. These are 2 function calls that are responsible for 5% of all of the data center cycles. And they said that this is part of the data center tax. And they basically said that the paper that I'm going to describe, actually, which was published before their paper, is a good direction to explore to minimize data movement in systems. So let's take a look at how we do bulk data copy today in systems. So I'm not going to talk about initialization because initialization is actually a special case of copy. In order to be able to initialize a row, many rows in memory, you can write some data in one row and you can copy that row to all of the other rows. So fundamental primitive is really copying. Let's take a look at how we do copying today. Let's assume that you have a 4 kilobyte page, the white page, and we want to copy it to this gray page. Today, we go through the processor. Basically, byte by byte, the source page goes into the processor, the destination page goes into the processor, you do the copy and write back the destination page. Clearly, this is high latency. You do multiple round trips. This is high bandwidth utilization on perhaps the most important bandwidth constrained resource, which is the memory bus. This causes cache pollution, but you could eliminate that today by doing this through the DMA, direct memory access engine. And this causes a lot of unwanted data movement, especially if you're initializing, for example. You basically move data for no reason, and the caches are ineffective because you're not going to touch this data anytime soon. So today, 4 kilobyte page copy going through the direct memory access engine, not even touching the cache hierarchy over here, takes about 1,000 nanoseconds and 3.6 microjoules. So if you give this picture to a 10-year-old child and ask the question, am I doing something wrong here? Maybe they will tell you, well, why don't you do this thing in memory, since you're not going to reuse the data potentially soon. This will be in low latency, clearly, because we're going to take advantage of the high bandwidth inside the memory. This will actually get rid of the data bus utilization over here and free the data bus for hopefully better uses. This causes no cache pollution, but you could have eliminated that today anyway. And no unwanted data movement. You move only the data that's necessary that you're going to touch. So I'm going to show you a mechanism that takes us 1,000 nanoseconds to 90 nanoseconds. If you optimize, you could do better actually, and 3.6 microjoules to 0.04 microjoules. And the idea is called row clone. It's a very simple idea. And in a DRAM subarray, at the very fundamental level, if you want to copy one row to another row, you can actually use a row buffer, which is the sense amplifiers inside the DRAM subarray, to be able to do this copy. And this is a temporary buffer. And the idea is very simple. It can actually be doable almost in existing DRAM chips. We didn't demonstrate that. Somebody else who used our infrastructure demonstrated, but I'm going to give you a reliable way of doing it. You design the DRAM chip such that you can support back-to-back activates. You first activate the source row, which brings the data into the sense amplifiers. Now the sense amplifiers are very strong. The size of a single sense amplifier is this 100 times the size of a single cell. Now you capture the data of the row in the sense amplifiers. The next thing you do is activate the destination row. Now this implicitly deactivates the source row and connects the sense amplifiers to the destination row such that the data you captured from row A is driven into the destination row. By doing 2 consecutive activates, you can essentially, with negligible hardware cost, do this copy with more than an order of magnitude lower latency and almost 2 orders of magnitude lower DRAM energy, essentially. Clearly, this happens if the source and destination rows are in the same subarray. So if you really want to take advantage of this, your operating system needs to be aware, or at least your programmer needs to be aware if you have a really good, diligent programmer. But if you want to take advantage of this in the general purpose domain, you need to solve multiple issues that I'm not going to go into. These are general issues related to processing in memory. But we also provide interbank copy support, which is good. Actually, we recently published works that are much better than what is depicted over here, and inter-subarray support that's much better than what is depicted over here. Essentially, you can make copies an order of magnitude faster and almost 2 orders of magnitude more energy efficient, let's say, in terms of DRAM energy. Okay, but you could say I'm actually cheating. Yes, I'm cheating, but I think data copy initialization is important. But this is also a mindset. Essentially, maybe we should be looking at specialized capability in memory by taking advantage of what memory is really good at. And I believe data copy initialization is what memory is good at. We're used to designing many accelerators over here, and we're used to programming them by now. Maybe we could treat memory as similar to a conventional accelerator and add specialized computation capability inside there by using memory in terms of what it's good at. Okay, now let me hopefully not cheat, and let me give you examples of primitives that you can use for computation as well. So similarly to copying and zeroing, we could do bitwise or, bitwise not, and bitwise majority, which is really the primitive that we're going to exploit at low cost by using the analog computation capability that's present in DRAM. And the idea is to activate multiple rows concurrently, and this performs computation due to the charge sharing properties of underlying circuitry. And you can actually get 30 to 60x performance energy improvement in different bitwise operations. And this was published in this conference. I'm going to describe the idea. And new memory technologies enable even more opportunities. You could actually do exactly what I described in new memory technologies as well. And there's a paper that is looking into that. But you could do even more because you can operate on minimal data movement. In DRAM, fundamentally, you're destructive. Whenever you read a row, you're destroying the data. You need to move the data at least to the sense amplifiers. But in emerging memory technologies, you don't even need to move the data to the sense amplifiers to be able to do non-destructive operations.
So again, as a student,
Yes.
if you have here functionally completeness, universalities, and you can do anything that an ALU can do, right?
Absolutely. Yeah, absolutely. That's what I'm going to get to. You're okay. Absolutely right in the end. So let me finish in new memory technologies thought. Some new memory technologies have crossbar. No, that's okay. No problem. I think that's a very good point, actually. Basically, this is functionally complete, as you can see, and or not. But I'm going to go into a little bit more detail. In new memory technologies, you could actually use the crossbar array structure to do matrix vector multiplication, which is important for machine learning workloads. And you could also be functionally complete. So some of the new memory technologies you could do, for example, bitwise NOR or bitwise NAND, which is functionally complete clearly. So, okay, let me give you the idea over here. How do we do in DRAM and or? And the fundamental primitive is triple row activation. Assume that these are 3 rows in DRAM, A, B, C. I'm showing only 1 bit per row. And imagine that one row is 8 kilobytes. And imagine that we could do this in 1,000 subarrays. So you could do what I'm going to describe in 8 million bits at the same time, assuming that you provide enough power to the DRAM, of course. Nothing comes for free. If you want to do computation, you need to provide enough power to the device, just like we're providing a lot of power to the CPUs today, right? Okay, the primitive is, if we had the primitive of triple row activation, you could concurrently activate these 3 rows. And based on charge channel principles, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So what that is in Boolean is a majority function, bitwise majority. So you're basically computing the bitwise majority of the cells, which means that you're doing bulk bitwise majority function across 8 million cells in the example that I provide. But of course, you could take out the C in this Boolean equation. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. So you could do bitwise OR and bitwise AND by setting C to the right values. And you could expose this to the ISA instruction set architecture. I'm not going to go into the details of implementation. You have to really use row clone to be able to take advantage of it. And to minimize cost, you have to actually move the data to special cells, designated area in DRAM. I'm not going to go into the details of implementation. You can read the paper. What is important is you can do AND and OR. But this is not functionally complete, as was mentioned. To be able to have functional completeness, you need a NOT. And NOT requires a little bit more effort. But fundamentally, in DRAM, you have the complement of a cell on the other side of the sense amplifier, which is not connected anywhere in the same subarray. But we basically add some more circuitry to connect the complement that you get to a special row over here. So I'm not going to go into details, but you can implement NOT. And in fact, NOT's performance is the highest, as you can see, compared to existing systems. You can get 50x performance improvement and almost 60x energy reduction. And OR are quite good. And on top of this, you can build other primitives clearly. And then the next question is, of course, what applications could be mapped into it? Since this is functionally complete with effort, you should be able to map a lot of applications, I believe all applications to it. In fact, we have work under review that looks at mapping many different applications to this bitwise majority function. But there are some applications that are more natural fits because they already do bulk bitwise operations. I'm going to give you examples very quickly. Database indices, for example, use bitmap indices. You can represent your database as many bitmaps, and you can operate on these bitmaps using and or operations. These are much faster today, especially in GPUs. Some folks have actually designed databases, especially a bitweaving database, to maximize the bitwise operations so that they can do queries much faster on GPUs. Microsoft has designed a web search engine in a very similar principle, basically, to maximize bitwise operations, DNA sequence mapping, encryption algorithms, and set operations. For example, set union, set intersection. If you represent your sets in terms of bit vectors, you can actually do a lot of bitwise operations. So let me give you an example from a bitmap index-based database. This is end-to-end query performance, of course, simulated because we don't have this device. It's simulation-based performance. And we see that end-to-end execution query, if you map it correctly to Mbit with a lot of programmer effort, of course, no question about that, you basically reduce the execution time of the query by 5 to 6.6x in this case. And the query execution time reduces more as the size of your database increases. So this is, you have basically database size scalable performance improvement, which is nice. If you actually port the bitweaving database that are proposed by other folks, by Jignesh Patel's group, we actually ported that to our Mbit engine, and we see significant, even more significant performance improvements in end-to-end queries, about 12x, for example. And again, we see similar scaling with the size of the data that you're dealing with. So this looks very promising, as you can see. I'm not going to go talk more about this. You can read the papers that we've written on this topic. And the most up-to-date paper that we've written is this in DRAM bulk bitwise execution engine, which also has a very nice DRAM background, which we written from scratch. If you're interested, you can take a look at it. This is part of Vivek Seshadri's thesis. But let me give you 2 other works that are not our works that have actually validated these results. So this compute DRAM work took our FPGA infrastructure that I mentioned earlier, and they basically showed that by playing with the timing parameters in existing off-the-shelf DRAM chips without any modification to the DRAM chips, they were able to show that you could imitate or mimic the back-to-back activates of row clone so that you could actually copy 2 rows reliably, one row reliably to another row in existing DRAM chips without any modification, just modifying the memory controller such that you can mimic this back-to-back activation. And they actually showed that this could be done reliably in many DRAM chips. We actually replicated their results using our infrastructure, and we see the same thing. And they also showed that in some DRAM chips, you could do these bulk bitwise operations by imitating these triple row activation, which is much more difficult to do, of course. So this is actually a very good proof of concept, in my opinion, because even though DRAM is not designed to support this row clone and Mbit type of bitwise operations, you could do it by modifying the memory controller in an intelligent way. Imagine what you could do if you actually designed the DRAM chip to do these operations in a reliable manner. And as I said, there are works that show that you could do these operations in non-volatile memories also. I'm not going to go into the detail, but essentially these operations can be done in phase change memory, for example. Okay, let me go into the next direction, which is exploiting 3D stacked memory very quickly. Basically, clearly this is very different. The previous approach was processing using memory. How do we minimally change memory? Here, we're going to be very opportunistic because these technologies already exist. There's 3D stacked memory plus logic. And these are actually under use today. High bandwidth memory, for example, is one example of this. Hybrid memory cubes is another example. Wide I/O technologies are another example, where you can have a logic layer that's programmable. And on top of the logic layer, you have many memory layers that are connected with true silicon vias at high bandwidth, low latency, low energy. And other true 3-dimensional technologies are under development. I call these true 3-dimensional technologies because they're more monolithic. And you can have many, many vias that are connecting the logic and memory layers, and you can mix logic and memory layers in between each other. Clearly, thermal constraints are an issue over here, but you need to overcome those thermal constraints somehow to be able to do powerful computation.
So one more interrupt, please.
Sure, yeah, please.
In my naive thinking, I thought that you implement computing on memory by having, table lookup to implement addition, subtraction, etc. So can you comment about this approach?
So that's a great question. We actually have a work under review that looks at computing using table lookups. I think that's a very good approach also. In DRAM, it requires a little bit more work. In DRAM, you can actually use your DRAM as lookup tables to actually do the computation. I like that approach, actually, but we haven't published it yet, basically.
Okay, thanks.
Yeah. But that's a very good approach. But there is a work that was published in Micro 2020 in October that uses that lookup table-based approach that you mentioned in caches, in large last level caches. So I would recommend, if you're interested, you can take a look at that. Okay, so these 3D stacked memories already exist, and basically we want to take advantage of them. And when we started our research on this topic, we actually had two key questions. What if we had the entire freedom in the world to change the system, programming model, etc., everything, so that we could maximize the performance of a 3D stacked processing in memory system? What kind of benefits do we get? And then, okay, of course, what if we don't have the freedom to change the system? What if we do just simple functional floating? So these near data processing engines, what kind of benefit we would get? And on the opposite extreme, what is the minimal thing we can do with these 3D stacked logic plus memory chips with minimal changes to the system and programming? And I'm going to cover all of these as much as possible, but let's start and see how much we can cover. Let's start with the maximal approach. And whenever you have a new technology, I think it's always good to look at the maximal approach and the minimal approach and explore the design space in between as well. So a maximal approach, I think, requires you to specialize somehow. And at the time, we were looking at graph processing. I believe graph processing is very interesting today. Bioinformatics use a lot of graph processing today. A lot of machine learning frameworks use graph processing. But graph processing fundamentally is bottleneck by memory. If you throw cores at the problem, you gain performance, but not commensurate with the amount of resources you throw at the problem. And fundamentally, this is because you have a big bandwidth bottleneck because you have a lot of random memory accesses and little amount of computation to cover for the latency of those accesses. And again, this is not true for every graph processing, clearly, and it's not true for all parts of graph processing, but this is common in difficult graph processing applications. So how did we try to overcome this problem? Basically, we designed this tesseract system for graph processing. I'm not going to go into more detail. It's a full system design starting from the logic layer and memory layers. So if you look at the logic layer of 3D stacked memory, you have these what is called vaults. Each vault has a DRAM controller that controls the memory on top of it, memory stack on top of it. And these vaults are interconnected with each other with some sort of network. And we basically add a very simple in-order core so that we don't violate the thermal constraints in this. And this in-order core updates the data that's housed on top of it, essentially. It can operate on data and can update the data that's here. So basically, data doesn't move. Data gets mapped onto these vaults. And whenever you want to update some node in the graph, you send a message to the in-order core that houses that data on top of it. That's the idea. So it's a very data-centric programming, distributed system-based programming, remote function call-based programming in the end. You basically move the computation to the data plus the intermediate values and the parameters to the data, which tends to be much smaller than moving the data itself in the end. So clearly, you send messages to the cores to actually compute on the data. And to be able to scale the system, you need to actually have more 3D stacked memory plus logic chips, because one is not enough. One can be, let's say, 32 gigabytes. That's not enough. In order to scale to terabyte levels, you actually need to scale more. So basically, the programmer needs to map the graph to these 3D stacked memory cubes, let's say. And then on top of that, they need to map the graph nodes to the vaults over here. And they need to, of course, that's graph partitioning is very important. And that limits the scalability of the system in the end, because you don't want to communicate across these devices, but you can communicate internally nicely. Ideally, you would like to minimize the communication to the node itself, to the vault itself. But I'm not going to go into more detail. Essentially, it's a distributed systems-based programming using remote function calls, and we have some prefetching mechanisms as well. I'm not going to go into details of the mechanism, but I'm going to give you a comparison points just to give you an idea of what kind of benefits you would get. Basically, clearly the system is different from existing systems, which have the processor memory dichotomy. Here, processing and memory are coupled in each tesseract device, and then you basically connect different tesseract devices and you use them as a graph processing accelerator. But this could easily be a machine learning accelerator because it's relatively general purpose. And you can see that 8 terabytes per second bandwidth is exposed to the cores that we have, as opposed to 630 gigabytes per second at the time we did the study. And overall, end-to-end performance improvement across 5 graph processing algorithms, including PageRank, for example, is about 14x, including all of the bells and whistles that we add. And we didn't optimize this a lot. Later works actually showed that by doing better graph partitioning, better load balancing, better scheduling of computation to the cores, etc., you could increase this performance improvement to more than 2 orders of magnitude. So there's a lot of work. The last one, I think, appeared in Micro 2019 that shows that you could do much better than we did. So I think this approach is very interesting, clearly. and I'm not going to go into this, but energy reduction is also very significant. We showed that you get more than 8x energy reduction end-to-end in these graph processing workloads. Later works improved this, and they showed you could get closer to 2 orders of magnitude as opposed to 1 order of magnitude over here. If you're interested, you can take a look at the paper. But clearly, this changes a lot of things in the system. We assume, for example, you can think of this as like a primitive GPU with only physical addressing. All of the computation gets offloaded to this graph processing engine that's like a GPU, and you need to program it completely differently from existing systems. And some people may go to the lengths of doing that. Many people will not, clearly. But even if one person does go through the lengths of doing that, it could be useful because GPUs evolved that way also, clearly, to the level they're at today. But okay, let's take a look at what can you get by doing simple function offloading without changing the system significantly. And I'm going to very briefly talk about this work that I mentioned briefly. We actually looked at several Google workloads, and we want to do this with consumer devices because consumer devices actually are very much constrained by energy, and processing in memory saves a lot of energy. We wanted to understand the data movement in these 4 key workloads: machine learning, framework, web browsing, and video playback and capture. And as I mentioned earlier, we found out that more than 60% of the total system energy is spent on data movement on common use cases. And we wanted to examine processing in the compute units and 3D stacked memory to understand what kind of benefit we would get. And we actually looked at limited area and energy budgets that I'm not going to talk about. We basically carefully designed these compute units. But the second observation is what enables us to take advantage of these compute units. Basically, a significant fraction of the data movement often comes from very simple functions. And we design lightweight logic to implement these simple functions in memory. I'm going to talk about what those simple functions are very quickly in a little bit. But you could execute these functions in a low-power core. You could execute them in fixed function accelerators. In my opinion, having reconfigurable logic is a good idea. In my opinion, you really need heterogeneity in the system. And overall, the takeaway is, if you actually do the hard work of finding those functions and offloading them, you get about 2x performance improvement and 2x energy reduction. It's not like the 13, 14x that we got by changing the entire system, but 2x is, in our opinion at least, it's not bad by just offloading some functions. Let me give you an example of some of these functions. Since machine learning is hot today, in machine learning inference, we found out that more than half of the inference energy is spent on data movement, and half of that data movement comes from packing and unpacking, essentially preparing data for analysis in one of the next layers and quantization of data. And these are simple operations. I'm not going to go into detail. Simple data reorganization operations with a very simple arithmetic. And quantization itself is a very simple operation, data conversion operation. It's employed in all neural networks, for example, that does shift, addition, and multiplication. So very simple operations, and we offload them. And if you look at the browser, you see other operations like compression, decompression, texture tiling. And in video playback and capture, you have more sophisticated operations, but we know how to design accelerators for them. For example, motion estimation, deblocking, and subpixel interpolation are other examples. And on average, if you offload them to the near data processing engines that we designed, accelerators, specialized accelerators, you gain significant energy reductions as well as performance improvements that I'm not going to go into. I gave you the high-level takeaway. Okay. On top of this, I think in GPUs, you can do this sort of function offloading. I'm not going to go into the details. You can have a main GPU very much bottlenecked by data, but you can have simpler GPUs in the logic layers that can do offloading of very data-intensive portions. And you can actually minimize the data movement between the main GPU and memory layers. And you could do that in a distributed fashion this way. If you're interested, we have a programmer transparent mechanism of doing that together with NVIDIA. And there's more on GPUs, and we have other mechanisms for accelerating pointer chasing, which is very important and latency critical. And I'm not going to go into some of these works. We have some recent works that actually look at FPGAs with high bandwidth memory, and we look at accelerating weather prediction modeling together with IBM over here. And one of the more recent works looks at, as I mentioned earlier, genome sequence analysis acceleration using approximate string matching. This is a complete algorithm hardware co-design. And we look at other accelerators mechanisms also. So very quickly, let me talk about this minimal approach, because I think this minimal approach is really key for adoption going into the future. And we asked the question when we first started the research, what is the minimal thing that you can do to take advantage of this processing near memory using 3D stack memory? And what does minimal mean? Minimal cost, minimal changes to the system, no changes to the programming model. And the idea in hindsight is very simple, I think. Basically, we add instructions into the instruction set architecture that are going to be executed like any other processor instruction that we execute today, except the processor has the ability to potentially offload these instructions to the near data processing engine in a 3D stacked memory. And the restriction we add is this instruction operates only on a single cache block because we don't want to deal with the data mapping problems of more than one cache block being mapped into potentially multiple memory modules. So a programmer or a compiler emits these instructions, for example, that look like normal instructions. And this doesn't change the sequential execution and programming model. This doesn't change anything in virtual memory. You don't need to sacrifice virtual memory. In fact, virtual memory is one of the big headaches, I think, in processing somewhere far away from the processor. Minimal changes to cache coherence and no need for data mapping. Again, and the other key idea over here is you dynamically decide where to execute this PIM-enabled instruction based on simple locality estimations. I'm not going to go into the details, but you may wonder what these instructions may be. Again, somebody needs to design these instructions. I believe reconfigurable logic and a customizable ISA that can provide on-the-fly instruction modification could be very useful here. But these are some of the instructions that we added. Euclidean distance computation, for example, is very useful for stream clustering. Dot product clearly is very useful for machine learning. Some hash table probing instructions, histogram bin indexing, etc. You can see that could be executed. And the takeaway, okay, I'm not going to go into details because we don't have a lot of time. We looked at interesting workloads. You could always look at more interesting workloads. But overall, we found out that you get about 47% average speed up with large input data sets and 25% energy reduction with large input data sets. As your data sets become smaller, as they fit into the caches, you want to do the processing inside the caches, for example. But this mechanism can adapt to that. Okay. So this is, I think, this brings me to the adoption of a new paradigm. Clearly, processing in memory can be disruptive because it changes a lot of the way. In fact, it changes our fundamental way of thinking about computation, in my opinion, because it becomes more data-centric. But this means that adoption is not going to be easy also. And I think that's true for any new hardware, but I think processing in memory is a special place because we're very much used to, ingrained in our thinking in a processor-centric way, in my opinion. So these are 5 barriers to adoption of processing in memory in my mind, and most of them are related to software and system support overall. So what is the functionality of processing in memory engine? What kind of applications and software can be written to different styles of processing in memory, processing using memory, processing near memory, for example? How do we change the algorithms to be able to take advantage of it? Ease of programming, how do we support eased program interfaces, compiler and hardware support to ease the programmer's job? How do we provide system support to make this more general purpose? Data coherence, we didn't tackle that, although we have some mechanisms for this. Virtual memory, I think, which is one of the hairiest parts. How do we support virtual memory? How do we design runtime systems and compilation systems for adaptive scheduling of code, data mapping, and access and sharing control, potentially security issues? I'm not going to talk about these. Clearly, there are a lot of things over here. And how do we design infrastructures to assess benefits and feasibility? And how do we make it available for people who are both designing these systems as well as programming them? I believe all of these need to be solved, and all of these can be solved with a change of mindset. And I think the mindset change really needs to be moving from processor-centric to data-centric. In the end, we need to revisit the entire stack all the way from algorithms to devices. We don't need to do that immediately, but we need to be doing the research to do it. And I believe we can get there step by step. For example, row clone, once it's implemented in chips, for example, or even in existing chips, someone can exploit it relatively easily. And maybe some of those solutions can come after the hardware comes. And if you're really interested, we have written some survey papers that survey the state of the art. We actually have a newer version of it, which we're going to put on archive soon, that talks about some of the research issues related to this, as well as adoption issues. And this is a more software workload and programming driven version of that. And one of the good things is there are people who are working in industry who are actually designing these things. So this is actually a chip or DRAM module that's recently designed by a company called UPMEM, who they're based in Grenoble in France. We actually collaborate with them. We actually analyze their chips. And what this chip does is it actually has what's called DRAM processing units in each of the banks of memory. And these DRAM processing units can access the bank with high bandwidth, low latency. So in a sense, it's not processing using DRAM. It's actually putting a processor inside the DRAM, but it's not a very sophisticated processor. And if you can actually partition your data well, and if you can actually minimize the communication between different banks, you can get very high performance improvements from these chips. And this is real today. We've actually tested real software that we wrote on this real hardware. And this is very promising because this is perhaps the first real commercially destined processing in memory hardware that I know of. And this happened in 2019, and the hardware shipped in 2020. But clearly, I think we need to solve a bunch of challenges that I'm not going to talk about, that these are some of the works that have been tackling some of the challenges that we've been discussing. And in the end, I think the challenge and opportunity for the future is how do we design computing architectures with minimal data movement, more data-centric architectures. So this brings me to the end of the first and the most major part of the talk. Depending on how much time we have, we can spend 5 minutes and 3 minutes here, or 0 minutes on both, and we can just jump to the conclusions. I will leave it to Martin or anybody else to decide at this point. Any thoughts?
Well, I'm fine either way. I have time, but I don't know about
Okay.
everybody else.
So what would you
love to
advise?
hear about the other sections.
Okay. So clearly 2 people are not the majority, although in some places they may be considered majority. Okay. So should I go on then?
Yes, let's hear about the others.
Yes, please.
Okay, so I guess I'm going to go on since I have heard more voices right now. Not the majority, but I guess enough people who are interested. Okay, so I'm going to not hopefully spend a lot of time. I mean, in an ideal version of this talk, longer version, this actually occupies a lot of time also, but I think these are also important, and these are synergistic with data-centric architectures. The reason why there's less time spent on it is I believe there's less research on this one and both of these. So let's talk about the second one. Essentially, today's architectures are not good at exploiting data to make intelligent decisions. So if you look at system architecture, especially hardware architecture design today, it's very much human-driven. But I think this is true for system architecture also. Humans design the policies, they dictate how to do things. As a result, we have many simple, short-sighted policies all over the system. And these policies do not coordinate with each other also. There's no automatic data-driven policy learning. There's no farsightedness. And there's almost no learning. Basically, the hardware controller for a cache, for a memory controller, for a scheduler cannot take lessons from its past actions. It's very short-sighted in the end. So the key question we ask here is, can we design fundamentally intelligent architectures? And this, I believe, requires to be data-driven in the end, because humans are, in the end, data-driven. Based on the data we get from interaction with the system, we adapt our decisions in the future. In the end, a machine learns the best policies, hopefully, how to do things, as opposed to humans dictating the policies. And hopefully this leads to sophisticated, workload-driven, operating condition-driven, changing, far-sighted policies, as opposed to fixed policies that a human has dictated. And this hopefully leads to automatic data-driven policy learning. And in the end, all controllers are intelligent data-driven agents that coordinate with each other as well, because they have intelligence built into them. Of course, this is a dream. The question is, how do we start? I believe we need to re-examine all of the controllers that we have in the system with this mindset. I call this the data-driven mindset, let's say. And I'll give you an example of the work that we have done about 13 years ago. It started in 2006, actually, when I was at Microsoft Research. We called this the self-optimizing memory controllers. And I think memory controller is a great place because memory controller is difficult to design today. And what the key thing we're going to target is, how do we schedule requests to maximize system performance? So why is this difficult? So memory controllers actually need to deal with many timing constraints, and human is designed these memory controllers to ensure that these timing constraints are obeyed. They need to keep track of many resources. They need to handle DRAM refresh, manage power consumption, optimize performance and quality of service, etc. I'm not going to do the laundry list over here, but there are reasons for this, which I'm not going to go into. And memory controller design is becoming more difficult going into the future, because memory controller in a system that looks like this is the center of the world. Actually, a lot of all requests go into the memory controller to access memory, and requests are becoming very heterogeneous. Memories are becoming really heterogeneous. So this is going to become a much bigger problem into the future. Even existing memory controllers do not measure up, as I'm going to show you in a little bit. And in fact, I'll give you an anecdote. Sorry for extending this, but I think this anecdote is very useful, in my opinion. Chuck Tacker, who was a Turing Award winner because of the seminal work that he had done in Xerox Alto system, for example, early PC systems in the 1960s. He's designed these very complex systems, and he was one of the first to design these systems. While I was at Microsoft Research, he was a technical fellow at Microsoft Research, and he was designing the DDR3 controller for the Berkeley emulation engine. And we had a lot of conversations back then, because we were actually doing a lot of work on memory controllers also. And I remember him saying that this is the worst thing he has designed in his life, this memory controller, because he has to consider so many things. And this is a person who is clearly very talented in terms of designing systems. And in the end, it's difficult, basically, for a human to do. It's difficult to design a policy that maximizes performance, forget about quality of service, energy efficiency, and other things. There are just too many things to think about, and humans are not good at thinking about large state spaces. And on top of this, workloads are changing continuously, and system behavior is changing, operating conditions are changing, so the constraints under which you're making these decisions need to change. And humans are not good at state spaces, but also they're not good at considering all of the possible conditions clearly. So our dream was, wouldn't it be nice to design a DRAM control that automatically found a good scheduling policy on its own? And that resulted in self-optimizing DRAM controllers. So clearly it's difficult for human designers to do this. So our idea was to use the machine learning, a memory controller that incorporates machine learning into its decisions, essentially. And we observed that reinforcement learning maps nicely to memory control, because memory controller happens to be a Markov decision process, and it can provide some convergence guarantees in a nice Markov decision process in classical reinforcement learning. And we designed the memory controller as a reinforcement learning agent. Essentially, it dynamically and continuously learns and employs the best scheduling policy to maximize long-term performance. So very quickly, this can go into a lot of detail clearly, but I'm not going to do that. All of us are reinforcement learning agents. And reinforcement learning was first developed in psychology. Pavlov's dogs were the first demonstration of it. That's written demonstration at least. Essentially, these dogs learn to associate the bell ringing with food coming. So they learn to actually, whenever the bell rang in the state space outside of in their environment, they decided to go to their owner to get the reward, which is food. Essentially, we're going to design something like this. The scheduler is going to observe the state attributes and schedule a command based on that and get a reward. And the reward function needs to be specified, of course. And over time, it will learn to maximize the long-term reward, not the short-term reward, by setting up the reinforcement problem in a relatively classical way, I should say. In the end, the scheduler over time learns to associate actions with a state variable or given state spaces, and it picks the action that maximizes the long-term data bus utilization, in this case, long-term reward. And I'm not going to go into the details of this, but it learns to associate system states and actions with long-term reward values. Each action at a given state leads to a learned reward. And you schedule the command with the highest estimated long-term reward value, and you continuously update the reward values for state action pairs based on feedback from the system. Of course, you need to design this in hardware, and there are versions of reinforcement learning that map nicely to hardware. It's not going to be as simple as the decisions that you do today, but nothing comes for free. You need to for intelligence, you need to provide some additional hardware. And I'm not going to go into details, but the difficulty here is really setting up the problem. The reward function is critical, and that's really important for the designer to do. The designer doesn't need to deal with the policy itself. The policy is discovered automatically, but the designer needs to specify the reward function, the state attributes. Some of this can be learned with advances in machine learning techniques over the last 12 years. This could be dynamic potentially, or this could be automatically discovered statically. Actions are relatively easy, in my opinion, because you know what action space you have in a memory controller overall. So, okay, let's look at the results. This is 12 years ago, as I said. We basically showed that you can have large, robust performance improvements over many human design policies. Basically, we tried to beat this memory controller as much as we could with looking at a lot of different combinations of state variables and different ordering that a human could potentially come up with, and we couldn't beat it. And it outperformed us a lot so far in the end. Its performance improvements were more robust also because it could adapt to different workloads that you could throw at the problem, because this is reinforcement learning, and reinforcement learning is nice because it's not supervised learning. It's unsupervised. As a result, it can deal nicely with conditions that are not seen previously, and it's less prone to overfitting, especially with the things that you can take into account. Okay, so clearly there are advantages to this, but there are clear disadvantages to this also. And difficulty is now designer's burden is completely different. The designer doesn't design the policy, but they actually specify different objectives and the state variables. Hardware complexity should be kept in constraint. But I think the most important thing is mindset and flow. So designer needs to take the mindset of, okay, I'm going to design a machine learning agent to take decisions. I'm not the decision taker. The machine learning agent should take the decisions. And that's a big leap, in my opinion, for a hardware designer. And there are multiple reasons for this big leap. One is, well, first of all, you don't know what's going on potentially, but there also a design flow. The hardware flow doesn't really enable you to test these designs easily. So I believe you need to really design the design flow and hardware testing flow to enable easier testing so that the designers can actually change their mindset as well. So there's more work to be done. But if you're interested, you can take a look at this paper. But in the end, I believe we need to rethink the design of all controllers to be this way, because that way you're actually, in my opinion, more fundamentally intelligent. Okay, so that's one example of data-driven, self-optimizing computing architecture. Let me move into the last one, which is data-aware architecture. So if you look at architectures today, they don't know much about the properties of the data that's thrown at them that they're processing. So what's a data-aware architecture? I define it as an architecture that understands what it can do with and to each piece of data. And there are clearly many, many properties of data that you can imagine. Basically, this architecture makes use of different properties of data to improve performance, efficiency, and other metrics. Let's take a look at some properties that I can imagine. Compressibility, approximability of a particular variable, locality, as far as the programmer can figure out, sparsity of the data structure, criticality of the data for a given computation, or criticality of the computation itself that's operating on some data, access semantics of the data, security properties, privacy properties that you care about, whether you care about the fairness of access to this data. So you can imagine many, many high-level semantic properties of data. And today, whatever you can imagine doesn't get communicated to the hardware. It actually doesn't get communicated even to the operating system because we have a funnel. And the funnel looks like this, basically. Even though we could know a lot of information, and we do know a lot of information, even the data types, for example, but we could actually discover a lot of other information also. We could make the programmers actually specify a lot of the information if there are some programmers who are willing to do that. In the end, we don't have the interfaces to communicate it downstream. So we've been looking at a lot of interfaces to make things more expressive between the software and the hardware. So software potentially can provide higher level program semantics into the hardware, and the hardware can make use of the data structure level semantics that is provided to it. And this could be done at the data structure level. So we have a mechanism called expressive memory, for example, or the virtual block interface, where you can actually express information about memory at the data structure level into the underlying hardware. I'm not going to go into the details of this, but this is a work that we published in 2018. And it argues for this richer semantics in the instruction set, general purpose instruction set architecture, so that we can enable these cross-layer abstractions. And this is an example from that work that looks at, that's a table essentially. It's an ugly table you can see over here in the presentation. But this gives you an example of what you can do. For example, in cache and memory compression, if you know the data type, as simple as data type, you could do much better. As simple as data properties, whether you have sparse data or dense data, how much sparsity do you have? Whether you have pointers or something else, you can do much more basically. In NUMA systems or hybrid memories, you can do data placement much better. And we're not even considering security or privacy or something even more sophisticated in this work. So this is a synergistic work that we did with NVIDIA. And specifically, we looked at a cross-layer abstraction, very similar to expressive memory, but we focused on just expressing locality properties of the data. And actually, as far as I understand, NVIDIA is going to employ some of this in their future products. I don't know when. But basically, the idea is to express the locality properties of different data structures using what's called the locality descriptor in a manner that's very synergistic with what I discussed. You can express, for example, whether you have inter-thread locality, intra-thread locality, whether you have non-uniform memory access locality, what kind of sharing properties do you have on this data. And if you actually explicitly express this, you can design the hardware architecture to do the data allocation and migration in a much better way in a GPU. And this shows that you could get significant performance improvements, like on the order of 50%. Don't quote me on it. It's something like that, depending on the data sets you have, of course. And I think hybrid memory management is another example where you could do much better by understanding the properties of data. Hybrid memory consists of different types of memory technologies that have different greens and different reds. And I think if you understand your data and express it much better to the memory controller and communicate to your memory controller, you can achieve the greens as much as possible while avoiding the reds as much as possible, because the memory controller can do the data management, data allocation, and movements intelligently based on the properties of the data that it knows, as opposed to properties of data that it has to discover, and it has limited scope to discover in hardware in the end. And one example of this is this work that we have done with Microsoft, which looks at a specific case of memory that's heterogeneous, and it's heterogeneous in terms of its reliability properties. So let me quickly go over this. Basically, applications and data have different vulnerabilities to memory errors. A bit flip is not equal, depending on where it happens. And in a data structure like what you're displaying on the screen, maybe you don't care about a bit flip. A pixel basically changes the hue of a color from one hue to another hue. Okay, it doesn't matter maybe. But in some other critical data structure in your operating system, where when you're scheduling a process, you get into a deadlock because you get a bit flip in the wrong part of your data structure. So clearly there are different levels of vulnerability to memory bit flips. And if you could somehow express this as a programmer, first of all, understand as a programmer and express it, you could design a much more intelligent and scalable heterogeneous memory system and map your vulnerable data to reliable memory that you designed to be extremely reliable, and map your tolerant data to low-cost memory that you designed to be relatively low cost and perhaps with minimal reliability error rate guarantees. And we did that together with Microsoft. We called it heterogeneous reliability memory. And you can see the design space in the paper. This is an abstraction of the design space. And we found out that you could actually do very well on a web search workload. You can get rid of a lot of the ECC, unnecessary error correcting codes that are employed in data centers that use web search. And you could still have very good reliability and availability guarantees. And I will refer you to that paper, but this is an example of a data-aware architecture, and there's a lot more to do. And this requires a cross-layer interface to specify the vulnerability of the data to error. Let me give you another example very quickly. This is clearly domain-specific architectures are designed to actually to communicate more about data into the hardware. But I think they also can go into a lot more in terms of how they can communicate in terms of semantic properties of the data. In general purpose domain, I think we need to do more. But this is one work that we've done more recently. We've looked at deep neural network, and deep neural network evaluation is actually very DRAM intensive, especially for very large networks. And this is very well known that some data and layers in deep neural networks are very tolerant to errors. And the idea we had was you could actually reduce DRAM latency and voltage on such data and layers. And you could match the error tolerance of the data to the error levels that you get by reducing the DRAM latency and voltage to unreliable parameters that are basic operating points that are not recommended by the manufacturers. But of course, to be able to do that, you need to understand how much tolerance you need to get in your data, and you need to map it to the underlying DRAM. And you could do all of this while still achieving a user-specified neural network accuracy, inference accuracy target by making the training of the neural network DRAM error aware. I'm not going to talk about this, but you need to be careful about how you do this. You need to ensure that your training takes into account the sort of errors that could potentially happen. Basically, this is an example of data-aware management of DRAM latency and voltage for deep neural network inference. Let me give you an example of this. So this is the ResNet 50. It's one of the popular networks that are used. And we analyzed the weights and input feature maps and looked at maximum tolerable bit error rate to achieve some accuracy target. And you can see that there's a clear distinction between different inputs and weights of the network. So you can have very low error. You can tolerate very low error in this weights and inputs. You can tolerate very high error rates over here. So if you know this information, if the programmer or somebody else, the runtime system, figures this out, and if they actually provide this information to the hardware, you can map more error-tolerant DNN layers to DRAM partitions with lower voltage and latency. And you could dynamically do that, actually. You could dynamically adjust the latency and voltage in the systems that we envision. So in this case, we have 4 DRAM partitions, as you can see, and you could map the data to the appropriate DRAM partitions that give you the tolerable, that basically obey the tolerable bit error rate requirements of the data. And if you're interested, this paper has a lot of data and real system demonstration of it also. You can take a look at it. Okay, there's more to discuss in terms of data awareness. This work, for example, looks at a data-aware way of doing compression so that you specify enough information in your compression algorithm such that you can accelerate the indexing that happens in compression so that you can accelerate sparse matrix operations. But I'm not going to go into details of this. If you're interested, this is another example of a data-aware approach. And I think this is a big challenge and opportunity for the future. How do we actually have more data-aware architectures so that we can co-optimize across the stack in a much better way by enabling these expressive architectures. And as I mentioned earlier, I believe data-driven, data-centric, and data-aware goes together with each other, because if you're data-aware, you can specify properties about your computation and how should your data be mapped, for example, to specific memory locations so that you can actually provide processing in an efficient way into it. So I think processing in memory can be much more easier if your system is much more data-aware. It can specify your computation. And I think by nature, having a data-driven architecture is having processing near memory, because in a sense, an intelligent memory controller that learns from its actions is doing processing to learn from its actions. Even though it's not doing processing to do computation, it's doing processing to actually do better decisions in the end. So I believe these three approaches are actually very synergistic. So let me conclude, and I'd be happy to take questions. I have time to stay. So we've discussed all three, thanks to folks who were willing to stay online. I think we have a very engaged crowd. That's great. Let me conclude. So I believe it's time to design principled system architectures to solve the data handling problem, which manifests itself as a memory and storage problem in the systems we design today. I believe we need to design complete systems to be truly balanced, high performance, and energy efficient, which will lead to intelligence, as opposed to systems that are processor-centric, human-driven, and component-driven. Instead of that, I believe we need to be data-centric, data-driven, and data-aware. And I believe all of these are mindset changes in addition to design changes and in addition to computing paradigm changes. So there's a big mindset barrier in all of these also, because we're not used to thinking this way in general. I believe we need to enable computation capability inside and close to memory. I believe all forms of inside and close to memory. And hopefully I've given you enough evidence that this can lead to orders of magnitude improvements and enable new applications and computing platforms like the genomics platforms that we don't have today, which I'm very excited about. And maybe enable a better understanding of nature as well, because I studied psychology as part of my bachelor's studies, one of my bachelor's studies. And while I was studying psychology in the late 1990s, psychologists were fascinated with computers as a paradigm for understanding nature. And I believe they've given up on that by now, because general purpose computers are not a good representation of how nature operates, because they're very processor-centric, whereas nature is much more different, I think, as people have realized. And other people are looking into neuromorphic computing architectures, for example, which is a closer fit to how nature does things, but that needs to be maybe more general purpose as well. And who knows what else this could enable. There's the ... I think to be able to do this, we need to be more data-centric, thinking data-centric, data-driven, and data-aware. And maybe this will lead to some principles that can enable much more intelligent machines. I'm not suggesting this is the thing that we want to imitate, but there are some things that this thing does, the brain and the nature does, that are much better than our devices do today, clearly. And we're much more capable of quickly learning some things, even though we may not be able to do number crunching really well. And to be able to fully exploit what I've described, in the end, we need to revisit the entire stack, all the way from algorithms to devices. And we need to do co-design. And we need to also revisit the theoretical foundations. Maybe, I don't know, 50 years from now, the theoretical computer science course will change in a different way. I believe to enable adoption, we need to get there step by step, though, and that's very important. And these are some good principles that I have actually discussed during the course of this talk without naming them. But I think more than all of these good principles that we will discover and we have discovered, we need open minds to actually enable this sort of systems. And again, I will point you to these two papers. If you don't want to read this one, there's a new version coming up soon, hopefully in a week or so, and this other paper. And if you, I guess this talk actually became the longest version of this talk that I delivered right now, so you can ignore this one over here, because I was expecting we would have only 1 hour, and I was expecting to skip the data-centric and data-driven parts. So in the end, I will acknowledge folks who have funded our research generously. Hopefully they keep funding us. And I will acknowledge, most importantly, to my collaborators and students and postdocs, and most importantly, my research group, whom you can learn more about in these links. Okay, and this is where I will stop. Thanks for tolerating the I guess high bandwidth talk. I'd be happy to take questions.
All right, Onur, thank you so much for this awesome talk, and especially for giving it so late on a Friday night your time. Everyone, please unmute and join me in thanking Onur for this great talk.
Thank
Thank you.
Thank
you.
Thank you.
Thank you.
I have two fast questions. I have two fast questions, what I assume, I mean,
Sure.
and you can answer them real short. I'm actually supposed to go to a thesis defense in the electrical engineering department. So my first question, do you think that computer science students should really understand the notion of functionally completeness?
Absolutely, I would say.
So do you think that this implies that there is more need to emphasize some of the digital logic aspects in the computer science curriculum?
I mean, in my opinion, yes. I think in the end, I'm a strong believer in what I showed you earlier. I'm going to go back to that slide. I think this opens up not only better understanding. This slide. I think this opens up not only new opportunities, but also much better ways of designing software, even if the paradigm doesn't change. I think students who become software engineers will understand the machine much better, and they will design much better software going into the future. Because I think at this point we don't have a lot of free lunch as well, even especially if the computing paradigm doesn't change. So I'm a strong believer in that. And I think in general, I see electrical engineering and computer science as a continuum. There are folks, for example, at ETH, I teach the freshman computer science class on digital design and computer architecture. And we start with digital logic. We start with transistor as a basic building block, and we build gates on top of that. We talk about functional completeness. We talk about Boolean algebra. It's essentially we build into computer architecture on top of that. And this is a freshman level class that we teach at ETH. I don't know if Martin took it when he was here. I'd be curious to know. It was actually, I bet he took it, assuming he took the freshman level computer science curriculum.
The ACM, I don't want to go deep into it, but the ACM is now de-emphasizing digital logic in the curriculum. But seriously, this was just a provocative question. So now to another thing.
I'm happy to disagree with ACM on this one.
So it makes it two of us, or maybe three in the department.
Okay.
So the next question is, I have a little bit of a concern about, I think, something that you said maybe in your first slide or second slide, where you said that human beings are concentrating on computation rather than data. You remember saying it?
Well, I think
it was in the first slide. So let me tell you.
Okay, let me go to the first slide. I'm not sure I exactly said that one, but I think what I said what I definitely said is human beings today are certainly. Okay, I don't know why it's not coming down. Okay, but certainly being processor-centric as opposed to data-centric in their thinking.
Yeah, so I would say human beings has a great capability to filter the data, so they don't need to deal with so much data. So I just wanted to point to an area of research which is called computation with words, where, let's say, if I need to park my car, I will not think like Tesla, but I will not have to process gazillions of bits just before I park my car. So this is again a provocative question.
No, absolutely. So I agree with that. I don't know if you're done, but I think we're in agreement, complete agreement here. I mentioned, go ahead.
No, go ahead. I'm sorry.
So what I mentioned was in terms of how they design systems, human beings are being very processor-centric. But again, as you said, I don't need a million cats to recognize a cat from a dog as a human being, right? But the system today is being designed in a way to amplify the data. I mean, for whatever reason, right?
And you only needed the 10 years boy to find out that there is a problem in the system of moving data to the computer and back. So we have some capabilities that the computers still don't have.
Absolutely.
And the last thing is actually, I really thank you for the presentation. And I'm actually involved in computation in the compressed domain. And so I may contact you because I think it's interesting.
Yeah, that's it. Actually, I'm very interested in that. We have some works without hardware support looking into that, but I'm very interested in actually looking into that. If you're interested in it, this could be a collaboration opportunity for sure.
Okay, thank you.
Thank you.
Hi, I really love your presentation as well. I have a couple questions.
Sure.
So first, I've heard that there's some complex branch predictors and processors that use machine learning as well. Would you consider this part of being data driven?
Yeah, that's actually a very good point. Thank you for pointing it out. I normally point it out in an even longer version of this talk. Basically, that's, as far as I know, that's the only example of limited form of machine learning employed in hardware. Some of Samsung's and AMD's branch predictors are based on perceptrons. And if you know about perceptrons, they're the most primitive form of representation of a neuron in hardware or software. And they actually use perceptron-based learning to correlate different branch directions with other branch directions that were taken in the past. So that's, I think, very nice. And as far as I know, that's the only example of actually implemented machine learning hardware that's used in systems. Now it turns out this is not the best branch predictor. It turns out a human-designed branch predictor is better, but within the constraints of branch prediction. Let me put it that way. This is a very latency critical part of the machine. But I think that's an excellent example, and there needs to be more research to be done to actually make these branch predictors much better.
Yeah, because I've also read about, I think it was the branch predictor they use on ARM processors, where it just assumes like one way is always preferred than the other, and that one is similarly performant. So I don't know how much faster you really get by adding machine learning there.
Yeah. So, okay, I have actually a lot of experience, well, a lot is maybe an overstatement, but I have experience firsthand on this one. So I don't know about the ARM processor comparison. I think ARM processor actually has the state-of-the-art Intel processors, for example, have very sophisticated branch predictors that do many, many things. And I believe actually it's shown that given a limited hardware budget, these very sophisticated human-designed branch predictors with some sort of statistical decision-making mechanisms that resemble machine learning outperform the perceptron-based predictor. But in the past, for example, when I was doing my PhD thesis, I did implement the perceptron branch predictor came out at that time from Daniel Jimenez and Calvin Lin at UT Austin. And at the time, there were some less sophisticated human-designed branch predictors. And my PhD thesis actually banked on having a good branch predictor. So I was motivated to actually use the perceptron branch predictor. So I implemented it independently of these folks who developed these branch predictors. And I clearly saw in a lot of applications, on average, 20% reduction in branch misprediction rate compared to the state-of-the-art at that time. So these things actually work, and they actually get very competitive. But humans have actually have become very, very creative in terms of how they can do branch prediction today. So there's this competition that's happening right now to figure out whether machine learning can beat. I think the disadvantage of machine learning is it's very data intensive, and branch prediction is a very critical part of the machine in terms of latency. So you cannot afford to make a decision in 5 cycles, for example, because you really need this decision in the next cycle. You can design a corrector predictor with machine learning, but again, you're very latency critical. So this is a place where machine learning can, I believe, benefit, but you need to be very careful in terms of what you're doing. So hopefully this was useful.
Yes, thank you.
Sure, you're welcome.
Did you guys take a look in particular at general parsing workloads?
What do you mean by general parsing?
So, for example, parsing JSON or other types of languages. I mean, I'm sure for processing DNA information, there's parsing there, but more generally.
Yeah. No, so that's a great question, actually. We did not look at parsing in general, but our accelerator that I mentioned, okay, how do I go to this over here? This text analysis accelerator, I call it text analysis accelerator. I need to find my slide over here. Okay, Somehow I cannot find my slide. Okay, I don't know why. Okay, here it is. Sorry. Basically, even though we did not look, I think this accelerator has applications in text analysis, because what we do here is actually use some algorithms that are developed for text analysis. The BiTAP algorithm, I don't know if you're familiar with it, for string matching. We actually adapt it to be much more powerful and adapt it so that we can accelerate it using processing near memory, using very specialized accelerators. And we adapt it to the context of genome sequence analysis. But what we do is equally applicable to text analysis as well, assuming your problem is approximate string matching with some allowable errors. I mean, it can work for exact string matching also, actually.
It could work as well for natural language processing.
So in my opinion, yes, but we did not really look at applications to be mapped. Clearly, you can see that this is very recent work, which was published last month. And I believe this accelerator and the algorithm we developed together with it can work for that purpose as well. But I think that's a really great point. If you have, I don't know if you're working in this area, but if you're interested, we'd be happy to help out, since clearly NLP is not our area of expertise.
Any other questions?
This meeting or presentation is being recorded, correct? Where can we find this video afterwards?
Okay, I don't know if that was a question for me, but
well, I don't
know. Sure. I think Martin is graciously recording it, and if he supplies it to me, I'm happy to put it on my YouTube channel at the end.
Sure. We can do that. I think Chelsea will have the recording.
Okay, that's great. Yeah, because I usually put the talks on my YouTube channel, including my lectures as well, and at the university, and I'm happy to do that. I believe this was one of the more comprehensive versions of this presentation, so it will definitely add to the collection.
So Martin, can you post the link to the presentation?
Sure, if Onur sends me the slides, I will.
Yeah, it's in the slide, so it's not easy to copy.
Yeah.
No, not immediately, just at some point.
Yeah, I'm happy to send the slides. Are you so of this presentation, right?
Yeah, it's a starting point.
Yeah, sure, of course. I'm happy to share the slides. I'll send them to Martin after we finish the talk, and whenever I get the video, we will upload it, and I will send the link to Martin as well.
All right, last chance. Any more questions?
Did you do PhD in the ECE or in the CS department in Austin?
In Texas, I did my PhD in the ECE department. Okay. Yes.
Yeah.
But my undergraduate education was actually in an EECS department, which was at University of Michigan, Ann Arbor.
Okay.
All right. Well, hearing no more questions, thanks again, Onur. This was awesome. I really appreciate you taking the time to tell us about all this very interesting work. Sure. And I'm really glad you could make it.
Yeah, thank you very much, Martin, for inviting me. And I really enjoyed the questions from the audience. And clearly they're interested, so they stayed.
Yes, that's a good sign.
That's a good sign always.
Yes,
clearly, I didn't RowHammer them enough.
I think you broke a record in terms of participants that are willing to stay beyond the 1 hour. So, so really, thank you. By the way, my son is now an assistant professor ECE in UT Austin. So.
Oh, okay. I see. In which department?
ECE.
ECE, okay. Well,
Yeah.
great. Yeah, thank you for your comments and questions.
Oh,
And I'm
thank
happy
you. It was very interesting.
Yeah, thanks.
Okay.
Okay, bye.
All right, Onur, I'll send you the link, and hopefully you can send me the slides, and then I will send it out to everybody.
Yeah, I'll do that right away. Thank you.
Awesome. Thanks so much. Have a great evening, everybody.
Yeah, you too. Have a good day and a weekend.
Bye.
Bye.